recording. Okay.
Okay. So good afternoon, everybody. I'm very happy and honored to be here today to introduce you Sven Leyffer. He's a Deputy Division Director and Senior Computational Mathematician in the Mathematics and Computer Science Division at Argonne National Lab, which he joined in 2002. And in fact, Sven is Argonne Distinguished Fellow. He's also a Science Fellow and Senior Fellow of the University of Chicago. And he's internationally recognized for his contributions to nonlinear optimization, with particular expertise in mixed integer nonlinear program, derivative-based algorithms for constraint optimization, and their applications in engineering, energy systems, and operations research. In 2006, Leyffer, along with two colleagues, received the Lagrange Prize in Continuous Optimization. In 2016, he received the Farkas Prize from the Informs Optimization Society. And on the top of that, he has a long and impactful list of service to the applied mathematics profession, including significant experience with SCIAN and ICIAN. He was, for instance, SCIAN president from 2022 and 2024, ICIAN secretary from 2015 to 2022, and presently he is president-elect of ICIAN. He obtained his PhD in 1994 from the University of Dundee in Scotland. He has numerous editorial appointments of leading journals. And, just check it today, the Google Scholar profiles. He has registered around 12,179 citations, age index 44. So we are very honored, and thanks, Sven, for accepting our invitation. It's really an honor for us to have you here. Okay?
Okay. Buenas tardes, estimados profesores. So I just wanted to show that I read the Slack. So one of the things I like to tell people when I give a talk is that I'm very happy for you to interrupt me, to tell me if I'm too fast or too slow. I'm also grateful to Liliana and Juan for inviting me and giving me this opportunity. I think it's wonderful that you have a sort of international gathering meeting where people can participate, and I wish we had more of these. So I'm going to tell you a little bit about combinatorial optimization problem, and in particular, I'm going to talk about topology optimization. And here is the first slide that's going to give you an overview of the talk, but also give you the punchline. So you only need to pay attention to one slide, and then you've got all the ideas from my talk. So we're interested in solving topology optimization problems, and they arise in many applications in additive manufacturing. They arise in, for example, 3D printing of wings or other structures. The example that I will concentrate on today is a topology optimization problem that's kind of a toy problem of an electromagnetic scatterer. So I'll explain this problem a little bit more in a moment. But just to show you the picture here, you have an incident wave that travels from the bottom towards the top. It's a 2D equation, and we design a scatterer, so that's a 0-1 pattern of material that we place in this obstacle. And then what you see on the left here is the magnitude of the superposition of the incident wave, that the wave that travels up, and the refractive wave that's refracted from this obstacle. And in particular, we're interested in minimizing the effect of this combined wave over here, where we're trying to hide material. So it's it's an interesting problem, it's a very challenging problem, and it's a very good test problem for our algorithms. It's challenging because if we discretize this problem, so here we're in D = 2, so we have 2 spatial dimensions, but we could imagine doing this in 3 spatial dimensions, then we very quickly end up with a massive number of binary variables. So in this example, for example, if I zoom in every pixel you can place one of three materials. Actually, you either place no material, a lighter material, or a heavier material. And so this design in this example that I showed you is a 256 by 256 scatterer. So that's a massive number of binary variables. And if you solve optimization problems with binary variables, then you quickly realize that the complexity grows exponentially. And you often find that when you solve these problems, you get branch and bound trees where you start off at the root node solving a continuous relaxation where you pretend your variables are allowed to be anywhere between 0 and 1. And then you pick one of those variables and either set it to 0 or to 1. And then you repeat. And with this algorithmic idea, you generate these branch and bound trees. So here every node corresponds to an optimization problem that you solve, where some of the variables have already been fixed. And the further you're down in this tree, the more variables have been fixed. And just for reference, the green nodes here are nodes that you could solve. The red nodes are ones where you found solutions didn't exist. And what you see is that these branch and bound trees blow up exponentially in many cases. And so this is actually not a way, so that's why we can't solve these problems. However, this talk, I'm going to tell you about two methods that will actually solve these problems. I tell you at least about one of these methods. And these two methods are very efficient in the sense that they scale just in the number of these discrete variables. So it's a much, much better scaling law. And one of them is a very simple rounding heuristic that I'll explain to you. And the other one is maybe a more sophisticated trust region algorithm. And so you might think those are just hokey heuristics because they're not searching these branch and boundaries. They're not leveraging this technology of mixed integer optimization. But there's this surprising result that goes back to colleagues in Germany that can show that you get global convergence. So in particular, as you refine the mesh, so if you introduce, in a sense, more and more of these binary variables, you're making the problem harder for these algorithms here. But under mesh refinement, you can show some asymptotic convergence, which I think is really interesting. And it shouldn't be that surprising because if you have lots of binary variables that contribute to a solution, then it probably doesn't matter where each individual binary variable lies. So I'm going to tell you about these two methods. I'll outline how this global convergence proof works, and hopefully we'll have some fun along the way. But this is all you needed to know about my talk. So you can now switch off. And in about 2 hours, I think you can watch the game. You can watch England play Argentina. So here's the outline of the talk. I'll tell you about this topology optimization problem, and then I'll concentrate first on this optimal rounding heuristic. That's the first class of algorithms. And then the second class is applied when the first method doesn't quite work, and that's a trust region idea. And this turns out to have a bottleneck, a particular bottleneck that I'll tell you about, and we can handle this bottleneck by developing new randomized integer optimization approaches that we've recently developed here. Okay, so here's a sort of quick primer on topology optimization approaches. So I'm going to distinguish this from shape optimization. I'm not going to look at shape optimization. I'm just going to concentrate on topology optimization. In shape optimization, we assume that we are given the topology of the design that we want to build. So for example, here's a design of a cantilever beam that might be supporting a bridge structure, for example. And you're given in topology, in shape optimization, you're given the number of holes that you have in this design, and you're now reshaping those holes so that you can support a certain load at one end, for example. And there's a lot of methods have been developed for this. Instead, I'm going to look at topology optimization, where we don't actually know how many holes the structure has. And in this case, what we're interested in is, again, maybe, for example, a cantilever beam like this one on the left, which I took from one of Ole Zsigmond's papers. And you have this is supposed to support some load on the right-hand side. And basically, you're trying to either place or not place material in every element of your finite element discretization. So imagine you have an underlying finite element discretization, which I didn't draw here. And now in every element, you either place material or not. And Ole Zygmunt has this wonderful 99-line MATLAB code that's now over 25 years old. But it's a great primer. And it actually provides you with a very simple way of playing around with these ideas. And you can see that you can do that in MATLAB. But there's no convergence proof or nothing too rigorous for this. So we're trying to do more rigorous ideas. So that's the problems that I'm interested in. And here's the specific problem that I'm going to look at for this talk. So I'm going to look at the topology design of a cloaking device or scatterer. And I'm going to have an incident wave that's down here. So this is the magnitude of my incident wave. And I call this incident wave or target wave U0. So that's something that's given to me. And that might be the wave for which you're probing a region. And this region omega, that's my computational domain. That corresponds to this region here. In this domain, I'm going to have a small subdomain, omega hat, in which I can either place material or not place material. So that's this binary restriction that I have. I have a function in this domain that takes either 0 or 1, or 0, a half, and 1 in later examples. But I cannot take fractional values in this domain. And then the goal is to somehow cloak or minimize the superposition of my incident wave and the wave that I generate in this domain omega 0 up here. So there's a domain omega 0 where I would like to hide something, and my objective function measures the integral magnitude of the superposition of these two waves. And what I'm going to show you is actually, I'm always going to plot this superposition for you. And in my domain, I also have Helmholtz equation. So that's a linear partial differential equation in complex variables. So there's real and complex variables. And I have some absorbing boundary conditions on my boundary that don't play any particular role here. And I'm not going to talk too much about how the PDE is discretized. I'm assuming that this is fairly standard. Now, an interesting caveat here is that the problem that I'm solving, I'm minimizing both in U, the state variables, and in W. That's actually a non-convex problem because I have these bilinear terms here. So this is actually a nonlinear equation if I consider it in both my design variables or controls and in my state variables, the U's. You can also think of this sequentially. I pick my W, and then I can solve Helmholtz equation to compute my states, and then I can substitute that solution up here into my objective. So that's the basic problem setup. And now I'm going to tell you how to solve this. And so the first method is going to be an optimal rounding heuristic. And this is going to have three very simple ingredients. I'm going to make the assumption that I can actually solve the relaxation of my problem. So I'm going to assume that if I allow my W, my control variables, to be fractional, then I can solve this problem. And that's a very reasonable assumption. We have lots of solvers for PDE constraint optimization problems, and we can solve this problem, and the relaxation is relatively easy to solve. And then the goal of this part of the talk is going to find a good rounding heuristic. So I'm going to start off with this continuous relaxation, which I call WC. It's in green because I can compute it easily. And then I want to construct a WB, which is my binary solution. And that's harder, so it's red. The first challenge that I need to address is I'm going to do this by rounding. And I only want to touch each element once. So I somehow need to decide an ordering of my elements. So here, for example, I have a mock-up of a finite element discretization with my finite elements, and I have my control elements in blue. So these correspond to the different W's that I have. So there's a W here, here, here that are constant on each of those blue cells. And the first thing I need to do is decide on an ordering, because I'm just going to go through these W's in one ordering once. The reason for doing that is because these methods were originally developed for optimal control problems that just had a time horizon. And so I want to leverage those ideas. And that's an idea that goes back to some work that Paul Manz did when he did his PhD with Christian Kirches in Germany. And so this is a very simple idea, but quite insightful. And what they observed is that they use space-filling curves. And these space-filling curves have some very nice properties that you can exploit when you're looking for convergence analysis. So in particular, here's one sequence of space-filling curves that work on 3 different discretizations, finite element discretizations, for example, a 2x2, 4x4, and an 8x8. And the nice thing about these space-filling curves is that if I look at the refinement, for example, of this first element, then if I follow the space-filling curves, the first 4 elements in my refinement correspond to the first element here as well. So I have some kind of order preserving, and it goes further. So again, this first element here, if I refine it, the next 4 little elements correspond to this refinement. And that seems like a very useful property to have, especially if we want to show some kind of convergence as the mesh size goes to 0. And so these space-filling curves gives us a natural ordering, and the ordering of my elements is preserved under refinement. And I also conserve weighted means. So if I look at the effect of this element, then later on a smaller discretization, then I have some kind of conservation of these means. And there's something that Paul can tell you more about, and that is that under this order-preserving decomposition, you can show some weak star convergence, which I'm not going to do here. So here's the simple rounding idea. I'm going to take my continuous relaxation. That's my first step here. Then I'm going to look at my space-filling ordering. I'm just going to follow this, and I'm going to do some rounding there. And I haven't specified the rounding yet. So the rounding is where the key ingredient lies. And this rounding is, I could do some simple rounding. So simple rounding would be to say, well, I look at my elements in my ordering, and whenever the element, the continuous one, sorry, there's a typo here, let's correct this. Oh, that should be a continuous one. If the continuous relaxation is larger than a half, then I round it to 1. That might be reasonable, but that turns out to be really bad. So in the first case here, on the left, you saw what happens if I round anything that's above a half to 1, you get this red curve. But now if I have a control that's just below a half, then the rounding would be always 0. And that doesn't seem to make sense. Or if I have an initial continuous relaxation, which I can show here, that's just above a half, then it's always rounded up to 1. And that doesn't seem reasonable at all. And it doesn't preserve, for example, the integral over this control if I'm constructing it. So here's an idea that's also quite classic now due to Sebastian Sager, who is in Magdeburg. And he had this idea of saying, well, as I do the rounding, I should somehow preserve the averages over a collection of elements. And so we're going to look at this algorithm that's going to compute, it's going to go through my elements just once in one ordering. It's going to compute a rounding residual. And on my first element, if k is equal to 1, then this sum disappears. And I'm just going to look at the fractional value here, which in this case is this value here. So here's a little example where I have my elements 1, 2, and so on to n squared over here. This value there is a half, up there is 1. And so what I'm going to do is, if this rounding residual that I computed there is greater than a half, I round it to 1, otherwise to 0. So in this case, this is less than a half, I'm going to round it down to 0. And so as I round this down to 0, what I'm going to do is I'm going to take this residual is going to play a role when I look at my next rounding residual. Now I'm going to look at the continuous relaxation that I've computed so far and subtract the integer value that I had so far. So I'm going to get a rounding residual now. This blue rounding residual is now all of this. And again, that's less than a half, so I round it down to 0. And so now at the next iteration, again, I took the rounding residual and saved it into my next element, if you like. And now at the next iteration, I realize this is larger than a half. So I will actually here, I'm in this part, I'm going to go round this up to 1. But now I'm kind of missing something in my, when I compute the next rounding residual, it's going to turn out to be negative. And what I'm actually going to do, what this algorithm is actually going to do, is going to redistribute some of the controls that it had here, the continuous controls that came from down here, and this one up here, and it's going to borrow it kind of into that next element. And so it does that. It again has a new rounding residual at this iteration. It's less than a half, so it's going to pile that into there. When it piles this one into here, it realizes that there's a little bit overgap, so it shifts it into there, and you're left with this last one that just gets put into there. Okay, so one way to think about this is actually of starting off with, instead of finite elements, think of having a set of glasses that you've lined up. So you've been to your football game, and at halftime, all the beer glasses have different amounts of beer in them, and you want to reorganize the beer glasses locally and redistribute them so that the beer glasses are either empty or full, so that you can take the empty ones back to the bar, and whoever ends up with a full glass can drink the full glass at halftime. And so this is a rounding that sort of satisfies this property. I'm kind of redistributing material that came from here, and then again here and there. And the nice property of this is that it preserves a local averaging. And you can also show that at the very end, once you've done the rounding, the error that you make, the integral of the error between the rounding and the fractional solution is at most a half, because you're either going to have a little bit left over, or you might be left over with some element in here, but it can't be more than a half. And that actually underlies, that's the convergence proof almost right there. So this convergence proof, I'm not going to give you the full proof, but I'll try to give you the insights. There's one important assumption that goes into this proof, and that is that if you look at the optimal control problem, I'm going to highlight this in red actually here. If you look at the optimal control problem, your objective function is independent of the controls. So this guy here, there's no W in it. That's very important. And so that's this assumption down here. That's a very critical assumption. And we'll see in a moment an example where this isn't satisfied. So this assumption is important because if you look at the proof, and so again, this is only an outline of the proof. I hope I kind of convinced you with the pictures that I showed you that if I integrate my rounding residual over time, and I compare the binary solution to the continuous solution that I created, then that's somehow bounded by a half times delta t. Delta t is sort of, or h is the step size that I take. And so that is something that's easy to show. Once you have that, you leverage standard techniques from either PDE or ODE theory to show that the states will also converge. So if you think of your states as being, in this case, time dependent, just time dependent, so they're not spatial dependence here, then the states that you would get for your continuous relaxation and for your binary variables, which are these two here, they also converge, and there's some convergence factor here that again has this factor delta t. And so that means that if I now look at the objective function value, if I now plug these two values into my objective, then the difference between the objectives can also be bounded by a delta. So in other words, the rounding that I do produces an objective function value that's almost optimal. And hidden in here is the fact that when I compute these states by plugging the controls into my ODE or my PDE, I solve my PDE or my ODE. I have ensured that I have a feasible solution, and then the objective function values don't differ by too much. And so this allows me to give this asymptotic convergence proof as delta t, or my step size, goes to 0, which is kind of a wonderful result. there's one caveat here, and this is one thing that doesn't work, and that is not a good assumption, and that's the fact that we assumed that our objective function does not depend on the state, or sorry, on the controls. And if I zoom into, I think it's this part over here, if I zoom into this part on the right here, then you see that the solutions that I produce are often these speckle patterns. And that's not surprising. If you remember the solution where everything was nearly a half, then the sum up rounding would just go from 0 to 1, from 0 to 1, and would just be a bang, bang, a shattering control. And so we observe that also in practice. And a problem with that is that these are not solutions that you can maybe implement in practice. They're not valid topological designs that you can implement. But you can get around this by doing some regularization. And I'm going to speed up a little bit while I'm doing something that I don't really know much about. And so one way to regularize these problems is to add a term to my objective function that penalizes the variation between zeros and ones in my controls W. And so that's, for example, I can measure the total variation that I have. And if I do that, then my objective function now will depend on my controls W. So the assumption that I had in sum up rounding no longer holds. And in fact, you can construct examples where you can show this rounding approach now produces solutions that are no longer as optimal as they were before. And so the convergence proof breaks down. But luckily, there are people who have thought about this. And so Paul Mans had this idea of using a sequential linearization approach. So the basic idea here is I'm going to explain this in the discretized setting, so not in the infinite dimensional setting. I'm going to discretize my PDE, and that then allows me to model my TV regularizer as an absolute value. So it makes a much simpler approach. And I'm going to develop a sequential linearized programming approach. And the idea is that I can use the discretized PDE or the discretized ODE to eliminate my states. So I can think of my U of W as being a function that's implicitly defined through this set of equations that I have. And so I can then think of my problem as a much simpler equivalent problem, where I'm now just minimizing over my controls W. My function f is now a little bit more complicated. Just for notation, I'm using the curly f when I think of infinite dimensional function spaces. When I'm in finite dimensions, I call it ch and fh to denote that this is now the finite dimensional equivalent, where I use some finite element discretization, for example. The good news is that because I'm I have access to all the PDE technology, whenever I do a PDE solve, I can also compute adjoints. That is, I can compute gradients of my objective function at the cost of an additional solve. So that's actually quite efficient. So I now have a way of evaluating a simpler problem. At each iteration of my method that I'm going to develop, I will have to solve a PDE and an adjoint problem to get a gradient. But that now allows me to put an algorithm together. And there's a sort of slight deviation there. I can model my TV norm now as the absolute values, the difference on each element between my controls, but that's not too important. What's critical is this algorithm down here, the sequential linearization algorithm. So that's the algorithm that you want to use in this case, where you start off at an initial point for your controls, W0, and you set up your initial problem. You have an initial gradient that you obtain by solving for your state variables and getting an adjoint so that you have a gradient. And then you solve a subproblem that now has this gradient or a first order Taylor approximation of the nonlinear part of your objective, but you keep the TV norm there unchanged. So you don't do a first order approximation of the absolute value, because that would not be a good approximation. And you solve this problem inside a trust region. So you have, you want a new point, W, that's not too far from your current point, as measured by this one norm, for example, with this radius delta K. And the one norm here is useful for binary variables because it's like the Hamming distance. It tells you how many of those binary variables you change it from 0 or 1. So how much of this design is changing on every iteration. And then once you're done, once you've found a step, you need to decide whether you accept the step, whether it's a good step or not. You can measure that by looking at the reduction in your objective function. If it's a good step, you're successful, then you would increase the trust region radius. If it's not a good step, then you reject that step and you shrink the trust region radius. So in the next iteration, you're closer to the current point, and hopefully your gradient provides more information, more useful information. That's a very simple algorithm. And so Paul implemented this, and it took him 2 weeks to actually run this algorithm. And most of the time was spent solving the subproblem. So remember, in this algorithm, each time we evaluate the objective function or we compute a gradient, we need to solve a PDE. But the PDE solves are almost negligible. Most of the time is spent in solving this linearized subproblem. And so even though this is a very simple optimization problem, very simple subproblem, this is really, really, really hard to solve. And so one of the state-of-the-art solvers there is Gurobi, and it took Paul 2 weeks on the biggest machine that he had available at his university. The nice thing is, one, you can show existence of solutions now because you have bounded variation. And if we zoom in, then this design looks like something that you can actually implement. And it looks a wee bit like one of the reindeer out of Frozen. So that was not what we intended, though. But the bottleneck we have now is that we don't want to wait 2 weeks for a design, and this is only 2-dimensional. So we really would like to do this in 3D and larger dimensions. And so we need faster solvers for solving these subproblems. And so over the last year or so, we've looked at using randomized integer programming solvers. So not solvers like Gurobi that give us globally optimal solutions, but solvers that allow us to get good solutions that hopefully are good enough for good enough designs. And this is work with a former postdoc here at Argonne, Dominic Young, who had this key insight that we can construct all that what we're doing in these algorithms. What we need to do is look over connected subregions. So in your topology optimization problem on a 2x2 grid graph, so the simplest graph that you can look at, you want to find out which of the connected subregions should you increase from 0 to 1 or decrease from 1 to 0. And so for this simple grid graph over here, I've plotted all the connected subregions over there on the right. So that's actually that's a large number of subregions. And so exploring all of them is prohibitive because it's a doubly exponential number. So the idea is to somehow look through these regions in a randomized way and find descent steps that allow us to do a more efficient algorithm. And so the basic algorithms that we're going to implement is again, this is a very simple algorithm. It's actually quite cool. So the problem we want to solve is given up here. That's the problem that we're interested in solving. So that's my subproblem, a linearized subproblem that I want to solve. I have a linear objective function, a linearized objective function with the TV norm that I'm minimizing inside a trust region over binary variables. So, but a lot of these binary variables. And so the basic algorithm is very simple. I'm going to select a move, which we call an up move, on which is a connected subregion. So one of those regions you had on the previous slide, where I increase my variables from 0 to 1. And all I need to do is ensure that I select an up move that reduces my objective function. And then if I can find such a move, that's great. I'm also going to look for a down move, one where I reduce my variables. So this is now a region S down, where on this characteristic set, I reduce my variables from 1 down to 0. And as long as they do downhill, this is a perfectly defined algorithm. I haven't told you how to select those down moves yet, or up moves. And you can show that the algorithm actually converges to the global minimum if there are no constraints. So if we didn't have these trust region constraints, then this algorithm will always converge to a global minimum. But of course, it's not a very practical algorithm at this point. The nice thing is that for a single trust region constraint, so if we have just this single constraint, and it could be a more complex constraint, then we can show that we can start at a solution that's at the center of the trust region. So we start from the solution WK, and then as we increase or change the solution gradually, we will, again, there exists a sequence of moves that go to the global optimum. So that's a nice property of this algorithm. The second property doesn't extend to the property if you have two additional constraints. So there was an additional constraint, then this no longer exists. So now I need to tell you how to construct these moves, and Dominic does this with what he calls a merge-split algorithm, where he constructs and changes rooted spanning forests. So here's a more complicated, a 3x3 grid graph. I'm not showing you all the possible connected subregions here. Instead, I'm just showing you 3 rooted spanning trees. So the roots of the spanning trees are the red dots. And all the connected subregions that correspond to these dots are for this dot, that's this region here, for this one here, those are the rooted spanning trees that you can construct from that. And then this one here, there's a set of regions associated with that you can generate from this rooted spanning forest. So the plan then is we start off with a rooting spanning forest, some rooting spanning forest. We pick out one of those rooted spanning trees and we modify it. We pick one of the subregions and we see whether that improves our objective function or not. If it does, we take the step and we move on. And so this gives us a natural way of, sort of a bi-level way of going through these spanning forests. And so I can then do things like I can pick a region that I move up. If I can move up, then I can merge it possibly with other regions, and that then corresponds to changing the structure of my spanning forests that I have. And so this is now a randomized way of looking. I can now create a randomized way of looking through this exponential number of regions that I have. And I'm going to look for moves that maximize the change in objective and minimize the change in the constraints. So they are sort of efficient vertices that I'm creating. Okay, so back to my problem, and I'm almost done. We implemented this using Phoenix as the PDE solver with mumps for solving the linear systems. The meshes were not terribly big, up to 1024 by 1024. We use this algorithm and we implemented with 2 mixed integer solvers. One is Heis, which is an open source mixed integer solver that's developed by Julian Hall at the University of Edinburgh. And the other one is our merge split implementation. And we ran this on a fairly standard machine with 72 cores, but we were just parallelizing the runs, not actually running each run in parallel. So this is still a sequential solve. And so the timing results here are, you can see 2 sets of results. So Heis is in red. And as you increase the problem size from 32 by 32 to 256 by 256, the sort of solver side, this sort of grows exponentially. Maybe you expect that. And then for the merge split, for the randomized algorithm, the solution size doesn't grow quite as much. And if you zoom in, if you have better eyesight than me, then you can see error bars on these because we ran these algorithms, because they're randomized algorithms, we ran them 5 times, and we're reporting the average solution time there. And doubling the number or the mesh size n roughly increases for us, it roughly increases the solution time by a factor 3 to 5, which is what you would expect because you're basically increasing the problem size by a factor 4 as you're doubling the size. This is just to show that who gets the better solutions. So in many cases, we get similar solutions, and then sometimes we get better solutions than highs. And in particular, if we run our algorithm not just once, but maybe 10 times, we often find that we get better solutions than highs at much, much lower solution times. And we can solve much larger problems. This is just a look at the solutions that we generate. So these look different to the earlier solutions because we're looking at binary solutions here, not the 3 variables that I had with Paul. So we're generating solutions that all look quite reasonable. This is for different parameter values of the regularization parameter. So as you're increasing the regularization parameter from left to right, you're getting solutions that look more regular. And so this is increasing the alpha in this direction. And so you're getting solutions that are not as jagged. And then from top to bottom, you're increasing the mesh size. Okay, so I think I apologize for being slightly over time. So we're looking at scalable randomized techniques for doing topology optimization. We're kind of exploiting ideas that mix trust region methods from nonlinear optimization with these clever ideas of having rooted spanning forests that allow us to randomly explore the possible moves in a clever way. We get very competitive solutions when we compare to the straight up mixed integer solvers, but we're orders of magnitude faster, and we can solve this problem efficiently now. And it generalizes to other graph-based algorithms. And I should really say that this is work that was really done by Dominic Young here at Argonne while he was a postdoc here. He's now at Lawrence Livermore National Laboratory, and by Paul Muntz, who's at the Technical University in Dortmund. And I'm grateful for the support by the US Department of Energy. And there's the Advanced Scientific Computing Research Office that supports my work. So thank you very much. And I'm happy to answer questions.
Thank you, Sven. Great talk. I think we can open for questions. If anybody has any question, we still have time for that. If not, I mean, you
That's
can.
okay.
No, I mean, you always can ask questions. Okay, I give some time, but I have some, at least some comments.
Oh.
It's open audio. Okay.
Yeah,
I don't
and
know
you
if
can
it's
also
open.
always contact me by email. I haven't given my email here, but if you're interested in discussing this, I can
Okay,
jump
no,
on the call.
I wanted to wait a little bit and see if anybody has any question. Otherwise, I mean, I see, of course, it's not my specific field, Sven, but I see a lot of connection with this, I mean, the approach, I mean, the general idea with inverse problems. I don't know if I know that optimization and inverse problems, they are all connected, you know.
Yeah.
So, for instance, what we call maybe topology design, as you mentioned in the beginning, for instance, one of the problems that I'm involved when we want to kind of estimate the magnitude of some radiation sources, okay? And I mean, one point is you have to, I mean, think about the problems in terms of 1 and 0. Something like there is the source or not, no source or source.
Yeah.
That's one point. Okay.
Yeah.
Then You mentioned, in terms of effectively, effectively computing the adjoints.
Okay, yeah.
The gradients.
Hmm.
So you do that based on the adjoints, that in general we do that. And of course, that depends on your operator. So in the case that you were using here, what is for you this very effective solver of the adjoint? How can you give me an idea? How do you evaluate these gradients? This is all numerical approximations.
So I don't actually know. That's something that's hidden inside Phoenix. So we
I
use
see.
dolphin adjoints. But from my understanding, there is an adjoint partial differential equation that you can set up, and it's always a linear differential equation. And
Okay.
one way to think of it, I think in the easiest case, and I'm really on thin ice, for the Laplace equation, if it's A times U equals F, then it would be A transposed Q equals something that you need to solve. So it's often very easy to set that up.
Uh-huh.
And
Because
you mentioned inverse problems, and I brought this up because for inverse problems, what you would typically do is you would say, well, I have some observations that I make, and so you maybe have a different objective, which might be something like
yes. Uh-huh.
minimize some measurement matrix
Yes.
times U
Uh-huh.
minus my data. You might have a term there, sigma inverse squared. And then you might have, so we're looking for W, you would have some regularizer. There might be sort of a prior here or
Yeah.
something. And so structurally, they're very similar problems in that sense.
Mm-hmm.
But you're right. For us, the key part is that we have these binary variables, and I don't know if that makes sense in an inverse problem.
Yeah. I think it is nice. We have some, in terms of the continuity, I see that like the second step that as you add that kind of regularization,
Mhm.
that you always have that in the
Yeah,
ideas of the inverse problems. And no, I just, and you also, think about inverse problems as one of the types of the inverse problems are, inverse design,
yeah,
but I think that the idea, I thought it was nice, is this thing about thinking of one and zero. Okay.
yeah.
So that's maybe that you can connect with what you are. And of course, I see all the difficulties that you have as you increase the mesh and everything. We know that since you have many variables involved, all this, the reduction that you got in terms of the order of, the convergence order is very important. And a final question. For this 250, you were showing these problems with 256
Mhm.
mesh. And then at some point, I think you mentioned something like three times or something. At the end, you had, I don't know if I got it well. 200,000 variables, something like that.
Yeah, so let me go there. Oh, sorry, it's probably in the wrong. Yeah, so we have what we do here is we have in every element, so it's a 256 by 256 mesh, and in every element we have three values.
Ah, I
So
see.
we have 0, a half, or 1. And so one way to model that is with three binary variables. You can probably
I
model it
see.
with you can model it with two binaries too, but we modeled it with three binary variables. And so
I
that's
see.
that's that's where this comes from. So you
Okay.
have times 3 means, and in every location it can be white, gray, or black.
And that's what you solve in that configuration, that software computer configuration that you mentioned in the
Yeah.
end.
No, in the one at the end, we actually went just for a binary design. So it's just 0, 1. So the designs at
Okay.
the end, sorry, this is going to make everybody dizzy now. Um, there we go. The designs at the end are strictly 0, 1. So
Ah, okay. That
those
then
are
you
all
have
binary designs.
smaller
And
number. Okay.
yeah, and what you see here is the effect of increasing the parameter alpha, which is the regularization parameter. So you increase it by an order of magnitude, and then
And that's
it,
that the regularization parameter is always something that maybe I don't know if I did not get well, but it's something that you really have to do some trials, I would say. It's
yeah,
not so,
yeah, yeah,
yes.
yeah. You
Okay.
want to do. I mean, I don't know about this. You might be happy with this design, or you might want a more, or even more linear design. And so
Uh-huh.
that's 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 the effect of the regularization parameter. I think there's a good. You can see you can see something here versus there. Sort of those things are.
Okay.
Okay.
Thank you very much. Again, if somebody else would like to ask some questions, otherwise you can contact Sven. And it was really great to have you here. Thank you very much again. And I think now it's back to you, Juan.
Thank you very much, Professor Sven, for your excellent talk. Thank you, Liliana. Now